Hello everyone, today I will explain the famous architecture DenseNet, which could be used to solve image classification problem or other downstream tasks, for example, image segmentation or image retrieval problem. Here is the paper. I will use the paper and the article which I wrote to explain the idea, and I will show the code. So here is the article which I wrote yesterday. For DenseNet, the main idea is very simple to understand. For example, here is the main architecture. Compared to the other architectures, I think it is easier to understand. If you already know the ResNet, and I think it is more easier for you to understand the main idea. For example, here is the input image. We notice that it is horse, and then it will pass the convolution. For example, convolution layers, and then pass dense block. The main idea here for DenseNet is there exists dense block. After the dense block, there are two. For example, is not just two. Is there? For example, here we call it transition layers. For example, here is transition layer, and then dense block, and then transition layer, and then the predictions. So for DenseNet, if we understand the dense block, okay, everything is done. Now I will explain for example, the dense block. For traditional neural network, we know that, for example, each layer connect the previous one. So if we have for example here, if we have 4 layers, 1, 2, 3, 4, and the total number of connection is 1 plus 1 plus 1 plus 1 is 4. So the total number of connection is 4. But for DenseNet, it's not the same thing. For DenseNet, each layer connect all the previous one. For example, here connect the input. This is 1. The number of connection for each layer is 1. And here, for the second layer, it connect the previous one and the input. So the total number of connection is 2. And for the third layer, it connect the previous one and for example here, the first one and the input. So that the total number of this connection is 3, and then is 4. So in this dense block, the number of connections is 1 plus 2 plus 3 plus 4, and then equals to 10. So the last one connect all the previous one. You can notice that there are a lot of connections. So here is the formula. For example, here, if we in a dense block, the total number of connections is 1 plus 3 plus, for example, until L. L is the number of layers. So we use 1 plus L times the number of for example, layers is L, and over 2. So it's the total number of layers for dense block. Here is the main difference between the DenseNet and the traditional network here. And now I will explain the dense block here, and I compare the dense block with ResNet. Here in this part, I will explain the detail of the dense block. First, I show the ResNet here. For ResNet, we know that for each layer is the connect the previous one, and we set a skip connection connect the previous one. So here we use plus, and we can notice that in fact there are two main differences between ResNet and DenseNet. For ResNet, you use skip connection and use plus here. For DenseNet, use, for example, all the connections and then use, here is not plus, it's C. C means concatenation. So here I wrote here, for example, for ResNet combine features through summations. Here is summation. For example, it sum all the values. It's not values between this one and the previous one. But for DenseNet, it uses concatenation. I will explain that in the following part. Now I use the, for example, this is the article, is a part of the article to explain the main idea in a mathematical way. For example, here, if we use HL represent, for example, the composite function. For example, we mean nonlinear transformation. We use batch normalization here and ReLU and pooling or convolution. HL represent, for example, this main operation. HL is the here we use. HL we use this part. For example, here I will explain HL or the transformation HL. For example, here. So for ResNet is for each layer. For example, if we have L represent the, for example, the layer. For example, if else layer, and then for the else layer is the, for example, is the function of the previous one and plus the previous one. So it's the function, is the operation of the previous. For example, here is the operation of the previous one. For example, operation of the previous one and plus the previous one. This is the operation of the previous one and the plus the previous one. So here is the mathematical explanation for ResNet. Now I will show the code for ResNet, and then I think it is more easier for us to understand the main idea. This is the residual block. For example, this which wrote in PyTorch. So in channel, out channel, and then kernel size and stripe padding, and I think it's easier for you to understand that. So here there's convolution and HeLU. So we use residual equals to x. X is the input. For example, x is the input residual. So output is the function of input, and then the output is the output plus. We use plus residual, which means plus x. So here is x. Here is the x plus, for example, x. So here we wrote here. This is the residual or ResNet. But for DenseNet, this is not the same thing. We said it's concatenation. It's a concatenation, which means for each XL is the function of all the concatenation of all the previous layers. So for example, XL is the function of the concatenation of all the previous one, x0, x1 until xl minus 1. I show the image. I think it is more easier for us to understand that. Here is the image. For example, this is the input. For here, x1. x1 is the, for example, here is the function of x0 is easier to understand, and x2 is the function of this one, x0 plus x1, and x3 is the same thing. So here I wrote that for x4 is the function of, for example, x0. We can notice that x4 is 0, x1, x2, and x3, and then it's a concatenation of all this one, and then we get x4. And then if we have x5 is all the concatenation, x0, x1, x2, x3, x4, and then we use this one to get x5. For example, if the input number of fish map we said channels are 2, 3, 3. Here is 3, and then for example here, after each part, if we also get 3 feature maps. So here after the first layer we'll get 3, this is 6, and then 9, and then 12, and then 15. And then so after each, for example, after each layers, the total number of the layers will be augmented. Or we said for example, the input of each layer is not the same. It will augmented. So we show that we detail for the H4 function. For example, for H4 function, we notice that here we use batch normalization, ReLU, and convolution. You can notice that for traditional neural network, we use, for example, ReLU, convolution, and batch normalization. Normally, batch normalization is after convolution. And here is not the same thing. Here is and I think is the third difference between this one and the traditional one. So here is H4. For example, if we get H4 here, we use batch normalization, ReLU, and convolution. Here we get H4. It is here, this one. So we already know that for DenseNet, it is not very easy to understand. And it is not hard to understand that. It's just use the concatenation. Okay, we already know that the traditional DenseNet, and here is the transformation of DenseNet. We call it DenseNet B. B is represent bottleneck layers. Bottleneck layers is focused on for this part. For which part is for this one? Okay, here the transformation between each layers. For example, here. Okay, I think this one we can use this one. This is more easier to show that. For example, in DenseNet, we already explained that this part use batch normalization, ReLU, and convolution 3 by 3 here. But for bottleneck layers, the author add, for example, another, part to change the number of the features here. Now we for example, we already, if we have L layers, for example, and for each layers there are K feature maps. So for example, here is, for example, L plus K, L times K channels, or we call it channels or feature map. It's the same thing. For example, the input, the total number of the input, for example, is L times K, and I think it's not hard to understand it. And then the author use another layers, for example, another transformation. It's not layers, it's transformation. For example, batch normalization, ReLU, and convolution to change the total number of the feature map or channels feature map into 4K. For example, we can use 4K here. We can use 4K convolution to change the total number to allocate to 4K. And then after the 4K, we use the this one. This one is the same as the previous one. Okay. Oh, okay. I think this is not clear. Okay. This one is same as the previous one. So this is the DenseNet. For DenseNet is just add this part, so it's not easy. It is not hard. My bad. It's not hard to understand. Now we explain another transformation, DenseNet C. C is for compression. Now we focus on transition layer. For compression, it is focused on transition layer. Transition layer, which means here is a transition layers. Here is the map of transition layer. For transition, the main objective of the transition layer is to change the size of the feature map, or for example, of the channels. For example, here, if we have, for example, for this one, for each channels, if the size, for example, here is 128 and 128. After pass, for example, the transition layer, we use 2x2 pooling. So here is 64 times 64, and after that is 32 times 32. So you can notice that here is smaller. Here is smaller here. So the main transition layer is change the size of the feature map or channel. So here, they also use for example, one by one convolution to change the number of feature map. It's just like this one. It's just one by one channel, one by one convolution to change the number of the feature map. For example, here, so we can use here. They also use a theta. Theta number is, for example, is between 0 and 1. If theta equals to 0, there's no, for example, is no change. It's just for each, for example, so for the input feature, and here the number of the channel is not changed. But if theta equals to 0.5, for example, here, if this one, if this one is k, and then this one is 0.5 times k after this part, so 0.5 plus k, so 0.5 times k. So here, in fact, I think we could use, we said it's k times l, and then I think with k times l is more clear. For example, here is k, after this one is k times l, and then we use 0.5 times l, and then I think it's more easier to understand that. So which means is the compression, the number of the channels. So here is the main idea. Now I will explain the code. For the code, I think this is I will show the code which wrote by someone else. So for the code, there are 4 main parts. First is the, for example, is a dense layer. Dense layer is the, dense layer is the, for example, here is a dense, each dense layer is a dense layer. So here is, for each dense layer, you use batch normalization, ReLU, and convolution, and then another batch normalization, ReLU, and convolution, and then use forward. For example, forward. For example, here we can notice that is the concatenation between x and new features. For example, the x is the input, and new features is the generation. For example, is the is transformation between the with is a transformation between we use x. So it's, we said if we have the this one and this one, if this one is the output and new features, and then we also concatenate the input. So all this one is the output here. After the dense layer, we can notice here is a dense block. Dense block is the For example, dense block is here. Dense block. Okay, we wrote dense block. Dense block is the we combine all the layers, so it's to create a dense block. For dense block, we can notice that if we have number of layers, for example, if we have here, we have how many layers? 1, 2, 3, 4, 5 layers. So we have, for example, number of layers equals to 5, and then the input features. For example, if they have input features, if we assume input features is 3, and growth rate here, growth rate we said is, for example, k. For example, after each for example here, after each we generate k feature maps. So here we set is, for example, k, and then if we assume the number is 4. So here if we assume if I is equals to 0, and then this one, the input features is the 3 plus the 0 equals to 3. And then if I equals to 1, and then it's 3 plus 1 times 4 is 7. And then I equals to 2. 3 plus 2 times 4 equals to 11. And then 3. 3 times 4 equals to 15. And then for each layer, which means for each layer, the number of input augment from 3 to 7 to 11 to 15. So we use this to combine dense block. And then finally is the transition. Transition is the here. We use transition layer is transition layer here and here. So it's used batch normalization, ReLU, convolution. Convolution is 1 by 1. And the output features is, for example, is the parameter, and we use 2 by 2. So here is 1 by 1, so we can use this one to change the number of the channels, and we can use this one to change the size of each channel. So for example, if we explain that if before the channel is to 128 times 128. After this part is 64 times 64. Here, this one, the transition layer is the main idea. Is transition layer is to change the size of each channel. And then finally, this is DenseNet, which DenseNet is the combination of all the previous code. So for DenseNet, here the first one is create the convolution. Is just create the first part here. Here is create this one is there's no, for example, convolution 3, and then this is input 3 channels, and then given, for example, a parameter to for example to define the output, and then batch normalization and max pooling. Here is use max pooling, and then we create dense block. In fact, it is not dense block. It's here. It's all the part. It's dense block and transition layer. So it's all this part. The second part of the code is this one. So here, use block figure. For example, he used this one is, for example, block figures is a number of layers. 6, 12, 24, 16 is here. This number of layers changed. And then here use the this one dense block. We use dense block, and after this dense block, it add transition, and then to create that, for example, to create that, after create this one, this one, for each for loop, for example, for each for loop, we create this one, and the dense block and transition layer, dense block and transition layer, and dense block and transition layer. So here, and then for the last one, I notice that for the last one there's no transition layer. For the last one, it just add, for example, normalization, ReLU. So it's not just so we create this part is create list one and list one, and for the last one is just it's not create the transition layer, it's just create pooling and linear transformation. For example, you use ReLU, use normalization ReLU, and pass a linear. For each linear, we'll create number of classes, and then finally we use classification and output. Okay, here is the code of DenseNet. There are 4 main parts, and okay, today's finally is okay. I think I hope it's clear for you. Thank you very much.